Hello everyone, and thank you for your interest in this work. My name is Luis Antonio Hernandez, Master of Material Science, and I am currently a PhD student at the Instituto Tecnológico de Saltillo in Coahuila, Mexico. Before I start, I want to apologize if you hear some background noise. At the moment of recording this presentation, there is a very strong storm here in my city. The title of the work I am presenting today is Impact of Process Parameters on Peak Temperature in Underwater FCAWS Wells of A36 Steel. This research was developed at our institution with the collaboration of my co-authors, Dra. Rocío Ochoa, Dr. Gerardo Altamirano, Dra. Patricia Sheila, Dra. Perla Reséndiz. I hope you enjoy this presentation, so let's begin. Number 1. As introduction, underwater welding is a critical technique in industries like shipbuilding and offshore oil, but it is also very challenging because of the aquatic environment and the interaction of many process parameters. To deal with these difficulties and improve the weld quality, it's important to use advanced tools such as simulation. By predicting and analyzing the temperature reached during welding, we can better control the material's microstructure and improve consistency in the process. In this figure, we can see the classical schematical representation of the FCAW process, but when it is performed on the water, it is inevitably generates water evaporation and also a very drastic bubble formation. This physical and chemical interaction interfere with the arc stability, and as a consequence, they affect the heat transfer from the arc to the base material and also the resulting temperature distribution. So this figure tries to represent this in a very simple way. In second place, in the methodology section of this work, in this work we studied underwater FCAWS welding of A36 steel, a structural steel. The experiments were carried out in a transparent tank with a water column of 30 centimeters above the steel plate. So this can be seen here in figure number 1. We used an SF4 EMP235 welding machine with a semi-automatic equipment to record the main process parameters. Once a central composite design was implemented with 3 input variables, as we can see here in table number 1. The input variables were wire feed speed, voltage, and welding speed, and their factor levels -1 and +1 are shown in this section. To calculate the thermal behavior, we applied the method proposed by Isiklar and Girgin. This method is based on a 3-dimensional transient heat conduction model. It takes into account convection, radiation, boiling, and uses a Gaussian heat source to simulate the electrical arc. And the procedure was implemented and solved using MATLAB software. Now, let me briefly explain the main equations of the model. Number 1, the heat conduction equation. This equation describes how temperature changes in time and space, considering the density and thermal conductivity of the steel. In simple terms, it tells us how heat spreads through the material during welding. But it is necessary to establish boundary conditions. At the surface of the plate, heat is lost not only by conduction, but also by convection of the water and by the radiation. This boundary condition ensures that the model represents the real underwater environment. For the Gaussian heat source, the heat from the arc is modeled as a Gaussian distribution, meaning the highest energy is at the center of the arc and it decreases with the distance. This is more realistic than assuming just a uniform heating. In the natural convection, here we calculate the convection coefficient using the Rayleigh number. It depends on water properties and on the temperature difference between the surface and surroundings. This lets us estimate how fast heat is carried away by the water. And for the cooling rate equation, finally we use an empirical equation to calculate cooling rate. This equation was proposed by Suga in the late 90s, and recently was retaken and applied in underwater welding, and specifically in this type of process as flux coral welding self-shielded FCAWS. Together, these equations allow us to simulate the temperature profiles, the peak temperatures, and the cooling rates of, in this case, the welds. One says that in the section of results, the experimental measurements of current and voltage were fundamental to calculate the electrical power and the heat input. These values serve as a basis for estimating the peak temperatures and cooling rate. These results, let me put this here, these results show that the peak temperature varies significantly among all the samples. So this can be seen here. We can see this effect. So in table number 2, we show the amperage and voltage value recorded from the experimental welding. As the welding machine it's designed to maintain the constant voltage, the major variable or the major peaks we are going to find is in the amperage section. The results show that this indicates that the process is highly sensitive to a small variation in current, voltage, and welding speed. And it also confirms that the heat input alone is not a reliable predictor for peak temperature. But why? Mainly because of heat losses in water and the mentioned arc instability. On the other hand, electrical power showed a clear linear relationship with peak temperature. So we can see here as the electrical power, also known as watts, increase linearly with the peak temperature. On the other hand, regarding cooling rate, it decreases as the heat input increases. And also, this makes sense, since more energy results in a slower cooling. In a general form, as a conclusion for this work, the behavior of underwater FCAW welds is strongly influenced by arc energy, heat losses, and cooling rates. Also, accurate calculation of thermal parameters is crucial, not only to predict weld performance and ensure consistent quality, but also to guide process optimizations, improve safety, and support decision making in demanding underwater conditions. For this work, we gratefully acknowledge the financial support from Tecnológico Nacional de México to these two projects, 23227.25-P and 23076-P. And the authors, we also thank Consultores Asociados en Soldadura for the facilities and the technical assistance provided to carry out the underwater weldings. So, thank you very much for your time and your attention, and have a nice day.